Okay, so in the previous lecture, we talked about correlation, which allowed us to look at the strength and direction of the association between two variables. So now I'm going to talk about regression analysis, which I referred to as sort of correlation on steroids. And the reason for this is that while correlation allows us to make predictions based on the strength of the association between two variables, regression actually allows us to make very specific predictions, right? So we can actually make predictions about um, the specific score on an outcome measure or participant score on a particular outcome measure based on our knowledge of their scores on a particular predictor. So let me give you an example. Let's just imagine for a moment that we own an ice cream shop and we want to be able to plan for having enough ice cream based on the outside temperature. Now, we would expect that ice cream sales are going to be higher during times when it's hot as opposed to when it's cold. But it would be nice to be able to sort of make an estimate of how much ice cream we're going to sell based on the outside temperature, right? So we might say, well, we know that August has an average temperature of 90 degrees and June might have an average temperature of 80 degrees. And so how much ice cream do we need to have on hand during those months based on the different anticipated temperatures? And so linear regression will actually allow us to make a kind of a prediction about the average amount of ice cream we are going to be able to sell or we can expect to sell given a specific outside temperature. And we do this using a formula that's very similar to one that you've actually seen before, right? So we actually call it linear regression because it has its foundation in the formula for a line, y equals mx plus b, where m is the slope, x is a specified value for the predictor, and b is the intercept. So, but when we do a regression, we actually rewrite the formula so that it reflects what we're really trying to do here. And it's rewritten as y prime equals bx plus a. So in this case, y prime is the predicted value of y. Okay, so not the actual observed value of y, but the predicted value of y. B, based on our knowledge of a certain value of x. B is a slope, and the slope tells us the amount of change in y for every 1 unit change in x, right? So how much does y change? So how much does our ice cream sales change for every 1 unit increase in temperature, for example. X is a specified value on our predictor, so 90 degrees could be an example, and A is the intercept, which is the point at which the line would cross the y-axis, essentially at the point where x is equal to 0. And basically what regression analysis allows us to do is to compare how accurate our predictions are by looking at how much our predicted values differ from our observed values, right? So we are going to use observed values of x and y to make these predictions. So let me just show you what this means. So essentially what we're doing is we are plotting a line of best fit. All right, so here is our example again, ice cream sales along the y-axis, temperature along the x-axis, lower versus higher numbers, lower versus higher numbers. This is our intercept, which is the point at which the line is crossing the y-axis, right, where x is equal to 0. So each of these blue dots represents an observed value of y given a specific value of x, right? So let's just say this is ice cream sales when the temperature is 30 degrees, and these are ice cream sales when the temperature is 90 degrees. For instance, I'm not really specifically sure. All right, and so what here, this red line, which is our line of best fit, actually represents our predicted value of y given our observed values of x. So what regression really attempts to do is to draw a line that minimizes the distance between the predicted value, or this line, and the observed values. Okay, so if we look at this, this is just a few examples, right? We have the point of the line here, right? So this is a specific value of x, and here is an observed value. So this is the predicted value of y given a specific value of x, and this is the observed value at that same value of x. And what we can see here is that there's reasonably large distance. In fact, that might be, aside from I think this one, that might be one of the ones that's furthest away. On the other hand, in this point here, we actually have made a pretty accurate prediction, right? That our actual value falls along the line and therefore is almost identical to our predicted value. And we would expect, due to any number of factors, error is one of them, but the fact that perhaps temperature isn't the only explanatory variable for understanding ice cream sales. Like maybe people buy ice cream more often on special occasions. So we might see an increase in ice cream sales during Christmas, even though temperatures are going to be lower just because people like to buy ice cream when they're celebrating Christmas, as an example. So we wouldn't expect, if this were a perfect predictor, if temperature were a perfect predictor of ice cream sales, then we would expect to see all of these values to fall exactly on the line. If it's a good predictor, we should see the values clustering around the line. And if it's a bad predictor, then we should see the values to be more spread out, right? So they should fall further away. Closer to the line, better prediction; further away from the line, less accurate prediction, all right? And so that's really what regression analysis is allowing us to do, is saying how far are our observed values from our predicted values, all right? And then in some ways, this is very much like regression, right? So the more closely clustered they are to the line, the steeper the slope, the better the prediction of the better the prediction of the equation. All right, so let's give an example to try and make this make a little bit more sense. So imagine, for example, we are a farmer and we're interested in predicting egg production based on the number of hours of full sunlight that we have in a given period of time. And maybe the farmer does this so that he can kind of make a rough estimate of how much money he expects to be able to make given different times of year, given that the number of hours of full sunlight might be greater during certain months than others. So he's interested in finding out if the number of hours of full sunlight affects his chicken's egg production. For a week, he records the number of hours of full sunlight and the total number of eggs his chickens lay. He hypothesizes that the more hours of full sunlight, the more eggs he's going to get. All right, so this is a directional hypothesis. Not going to worry about that too much right now. And let's just assume that we've done all the calculations already because we have all the data, and we got a slope of 1.77, which basically means that for every 1 unit change in x, we're going to get a 1.77 increase in y, right? So every 1.77 change in temperature, or 1 degree change in temperature, we're going to get a 1.77 increase in the number of eggs produced. That's basically what that's telling us. Our intercept, so the point at which the line crosses the y-axis, is going to be 4.93 eggs. And so we want to know how many eggs will the farmer get if there are 3 hours of sunlight. Okay, so in this case, our formula y prime equals bx plus a. We're going to fill in our values here. So 1.77 is our slope, 4.93 is our intercept, and 3 is the value of x that we're interested in. And what this tells us is that if the farmer gets 3 hours of direct sunlight, he can expect to get an average of 10.24 eggs. But how about if there are 9 hours of full sunlight? So we can do the same thing. We can just plug the value of 9 in where the 3 was, and that's going to tell us that on average, when there are 9 hours of full sunlight, we should expect to get about 21 eggs. All right, so if we're planning in terms of income, based on our egg production, we can expect to make a lot more money on the days when there's full sunlight and a lot less money on the days when there is less full sunlight. So what does this actually look like? So in this case, we can take a look. I basically repurposed that graph. But in this case, when we have 3 hours of full sunlight here along the x-axis, we can expect to get an average of 10 eggs, right? Now, that doesn't mean we're only going to get 10 eggs, right? So the actual observed values of egg production is going to range from here to here, right? So these are the actual values, number of eggs that were produced. But on average, we're getting about 10 eggs. Similarly here, when there's 9 hours of full sunlight, we're getting a range of scores that are falling here, right? So we might get some eggs on some days, more eggs on days with uh, 9 hours of sunlight, and some days with 9 hours of sunlight where we get less eggs. Again, because this is not because of error in measurement, because of other factors. Maybe a fox got into the hen house one day, scared the chickens, and they didn't lay eggs, right? Something like that. But on average, we can expect about 21 eggs. Okay, so that's really what this line of best fit is telling us. And so as a shopkeeper or a farmer or as somebody who is trying to make plans um, for staffing of a restaurant, or planning for how much money we can expect to make or whatever, or to know how much ice cream we should have on hand, this kind of method can be really meaningful and helpful to us. Okay. So that's one of the advantages of regression analysis over correlation, but there's another, and there's actually three additional ones. So while correlation is really limited to looking at the association between two variables, regression analysis actually allows us to test models in which there is more than one predictor variable. And again, just like ANOVA can have an infinite number of groups, regression could have theoretically an infinite number of predictors. However, we're going to be limited, of course, by our sample size. So whereas the small r, the Pearson r, tells us the strength of the association between two variables, regression analysis will produce what's called a multiple R. It's a capital R, and that's going to give us the strength of the association between three or more variables, right? So remember earlier in the correlation lecture, I talked about the association between high school GPA and college GPA, right? And so our multiple R was going to tell us how strongly are these two things associated and in what direction. Is it positive or negative, right? And then we had our coefficient of determination, which told us what percentage of the variation between these two was overlap, right? Well, a regression analysis will give us a capital R squared, and that's going to give us the amount of variance explained in our outcome based on our two or more predictors. So in this case, we can add an SAT score, right? So high school GPA and SAT score are two of the main criteria used to determine admission to college. And so it would be important to know what percentage of the variation in college GPA is actually reasonably explained by knowing the person's high school GPA and SAT score. We would hope it's quite a bit. So the R squared for these two variables then would represent this entire area of overlap, right? So some of the area is just explained by high school GPA, some of the area is just explained by SAT score, and some of it is overlapping and explained by both. So in this case, it allows us to explain the full variation, which I guess you could say would be roughly just slightly shy of 50%, so maybe 35 to 40% is explained, right? This isn't real data, this is just made up data. But the final thing that regression will allow us to do is to look at unique variation in the outcome measure that's explained by the individual predictors. So for example, what percentage of college GPA is explained by knowing a student's high school GPA when we remove any variation that's due to SAT score? Similar, we can ask the question, what percentage of variation in college GPA is explained by SAT score when we remove any of the variation that can be explained by high school GPA? There are instances in which this might be something we would be interested in knowing. Okay, so that's really all there is to know about regression. And that's it.